Hello from PEMI Consulting. This is Philip Myers. This is a supplement to our first tutorial video on probability rules needed to work with a rate of occurrence of extreme hazards such as earthquakes, floods, tsunamis, and so on. This supplement has a table that you can download from the SharePoint site if you are a task group member, but you can easily make this table yourself or just email me and I'll send you a copy. The table will make it easy to understand the relationship between MRIs, annual exceedance probabilities, and the probability of exceedance for an exposure period for any number of years. Again, gambling comes to the rescue. There's no reason we can't have as many faces on a die as we want. Here we demonstrate MRIs and exceedance probabilities with a 100-sided die. I won't get into whether it is theoretically possible to have a fair 100-sided die, as that is a serious mathematical problem. So we'll just assume that our 100-sided die is fair. On each toss, the likelihood of a particular number coming up is 1 divided by 100. Suppose we are betting on a 1 coming up. It stands to reason that on average the number of tosses between getting the 1 is going to be 100. This is called the mean recurrence time or interval. We'll dub this the MRI. This can easily be proven by assuming that the number of tosses to the first occurrence of the 1 is a geometric random variable, and then using the laws of expectation. So we have that little p, the probability of getting the 1 is exactly 1 divided by 100. The reciprocal of the p is the MRI, or mean recurrence interval, which is, of course, 100. We learned in tutorial 1 from our friend Chevalier de Mere that if we roll the die, say 50 times, and we want to know what the probability of not getting a 1 on the 50 rolls of the die is, that it's 1 minus p raised to the 50th power. So the probability of getting a 1 is 1 minus the quantity 1 minus p raised to the 50th power. This calculation is easily done in Excel, and the answer is 0.605 or 60%. Therefore, the probability of getting the 1 in 50 rolls is 1 minus the 0.605, or about 40%. Why can we get away with this simple calculation to model something as complex as nature's extreme hazards? Because the events are random and independent, the simple statistical model for tosses of the die works. Recall that we chose the number 1 on the die. If we assign this to be some specific level of, for example, flooding or an earthquake magnitude of any given value that exceeds that level, then a very good model for this turns out to be the random process called a Bernoulli process, which we will talk about later. The Bernoulli process works extremely well for the dice problem, as well as earthquakes, floods, tsunamis, and other natural hazards. By thinking about these problems and keeping our special 100-facet die in mind, we can lock in the MRI and exceedance concepts. Don't worry about the answers now. We'll cover the easy way to get them next. Instead, consider the die, the problem, and what is really being asked. So in the first item, if you own a refinery, which is a multi-billion-dollar facility that performs many important functions in society and the infrastructure, how much exposure would you be willing to take over a period of time, like 5 or 50 or 100 years? Make sure you understand these questions and their implications to maximize understanding. I just want to point out a few interesting points about the 3/11 disaster at the Fukushima Daiichi nuclear power plant, which has turned out to be the most costly disaster in history, and where thousands of workers 10 years later are still cleaning up the site. The facility is pondering the best way to go forward to control the polluted water and thinking about releasing tritium, which is a radioactive isotope of water, into the ocean at a technically acceptable level, but there really are no acceptable levels by public opinion. The original tsunami was based on historical data, and they settled on a 3.1 meter value because of the 1960 earthquake in Chile. The actual tsunami was estimated to be 13 meters. In addition, it is known that the triggering earthquakes causing tsunamis in this region were of a magnitude comparable to the one that caused the disaster, that they occur every 1,000 years. Here are the tables that I promised. First, let's review the definitions. Consider that a single toss of a die is the passage of a year. Consider also that if your favorite number comes up, then the flood or earthquake exceeds some specified level. The die MRI was 100 because there was a 1/100th chance of your favorite number coming up. Pn is the probability of one or more exceedances in a consecutive n-year period. Let's call Pn the exposure probability, which is understood to mean over n years. It's the probability of your favorite number coming up in n tosses of the die. There are two formulas that can be used to build this table. The first one relates Pn to the exposure period n and the annual probability of exceedance, which is little p. The second formula is the inverse, giving the annual probability of exceedance from Pn and n. Looking at the table, we have row headings as MRI and P, which are reciprocal to each other. The column heading has n years, 25 through 5,000. These are arbitrary, but I tried to pick reasonable points within reasonable spans of time, but with the formulas you can pick any specific inputs you want. So for the example below, we see how to read the table. If we are concerned about a known flood exceedance and we are interested in the probability of an event that this flood will exceed at a particular site, then we can find out what the probability of exceedance for any period of time of length n. For example, for 50 years for an MRI, that's a 2% annual probability of occurrence. We can just read across to n for 50 years. And what we see is that the exceedance probability over a 50-year period for an event that has a MRI of 50 years is 64%. For 100 years, it's 87%. For 500 and above, it's virtually certain to occur. The table's been color-coded pink, where the odds are greater than even that the event will occur. This is arbitrary, but if I were an insurer, I would not like those odds. I'd want it to be less than 50% for the insuring period. In the next table, we are using the second formula to find the MRI given the exceedance probability over exposure period n. To illustrate, given even odds that the exceedance level will be exceeded in the next 100 years, we choose n equal to 100, and we choose the probability of exposure over that 50-year period to be 50%. We can see that the MRI is 145 years, and that is 0.007 annual probability of exceedance. In the last example, we show how to use the formula to get the ubiquitous ASCE 716 2% exceedance probability in 50 years exposure period. This is shown by the formulas. Probability is hard for nearly everyone, but stick with it and you will be head and shoulders above the masses in terms of understanding NATEC hazards. To get more information, I recommend you read the Probability Tutoring book by Carol Ash. Although there is nothing more advanced mathematically than simple arithmetic, I suspect you'll miss 40 or 50% of the quiz problems. But if you get through them, you will have a sound understanding of probability which will serve you a lifetime of problems. As task group members, I'm convinced you have to understand these basic concepts to be able to meaningfully contribute to our Herculean task of producing an API recommended practice or publication that not only collects the state-of-the-art in terms of best practices, but pushes the envelope. We have excellent people on the task group, and I expect great things from you all. Thank you.